Hello everyone. So it is my pleasure to introduce today Lukas Koch from the Max Planck Institute in Leipzig, and he will talk about functionals with non-standard growth and convex duality. Yeah, Lukas, do you want to share the screen or something? All right, so over to you.
All right, so thank you for the invitation. It's a great pleasure to talk to you today. So as was already announced, I want to talk about functionals with non-standard growth, and in particular, I want to highlight some of the connections of the regularity theory with ideas from convex duality. And this is based mainly on joint work with Jan Christensen on a paper that appeared on arXiv this week, actually. This paper in itself is based on an extension of early work from Jan Christensen, Carrozza, and Pasquale Di Napoli. And I will also mention some results from an upcoming paper by myself together with Jan Christensen and Christiana De Filippis. So I want to look at minimizers of functions of the form f of u, where we integrate some integrand f over domain omega. Omega for me will always live in Rn and will be a bounded set. And I want to stress two things here. So first, this function f, the integrand, I will assume to be convex at all times. And I will impose more conditions as I need them. And I do not allow for any x dependence of the integrand at this stage. So this is something that we're still looking at the moment. And of course, we know very well that this problem is very closely related to the L.Koch equation, which I've written here. And I want to point out that in terms of duality, some of the interesting quantity is exactly this derivative with respect to the z variable of the integrand evaluated at the minimizer. So this I will usually refer to as sigma. And then the L.Koch system says that the divergence of sigma vanishes. And for most of what I'm talking about today, it is actually possible as well to extend the theory to functions that depend on the Kf derivative, and then accordingly on the Kf derivative down here. And at times I will write down statements including the Kf derivative, and sometimes I will drop the Kf derivative to keep the notation as simple as possible. Now, I want to think about these problems in a regime where the direct method applies. And so then we know that we need some sort of quantified convexity bounds from below in order to apply the direct method. And in particular, the sort of bounds I will talk about today is I will talk about superlinear growth. So f of z is bounded below by a function theta, which grows superlinearly at infinity. Now, this is of course not quite the same as just saying that f itself is superlinear at infinity, but I can always add an affine function to an integrand f that is superlinear at infinity, and then it will satisfy this version of superlinear growth. If we want something weaker than superlinear growth, we could think about linear growth and accordingly BB minimizers. And in the context of today's talk, it will be useful to think about these sorts of growth conditions as demi-coercivity. So I will not just assume that f of z is bounded below by the modulus of z, but it will be bounded below by the modulus of z up to an affine function. So that is demi-coercivity. And then in the second half of the talk, I will also talk about situations where we apply second order growth conditions. And in particular, I will talk about some results for PQ growth. So there, the second derivatives are bounded below by an expression that goes like z to the p, and above like z to the q. And then when duality comes into the play, we will see something appear that we call controlled duality growth. And here the lower bound remains unchanged, but the upper bound we express in terms of the dual variable. So if you remember, this was the dual variable sigma. And now just to reassure you about the scaling on the right-hand side, so sigma sort of scales like z to the q minus 1. And so the right-hand side scales in terms of the original variables as you would expect. So it, as before. And in fact, controlled duality growth is a stronger assumption than controlled growth. So now I want to start by recalling some convex theory. And none of the convex theory that I will mention today is anything particularly difficult or novel. So you can find all of it in Rockefeller's convex analysis, for example. But some of the statements may be a bit hidden, or we've rewritten them slightly to fit closer to our context. So if I have a convex function, then I will denote by domain of f the points for which it's finite. And I will call such an f proper if f has a non-empty domain, and moreover f is finite on it. So in particular, f is not allowed to take the value minus infinity. And now, because I want to allow for functions that do take the value plus infinity, then of course it doesn't make sense to talk about this function being C1 or C2 anymore. And so the right notion of smoothness is something that is called essentially smooth. And f is essentially smooth if the domain is non-empty, f is C1 on the domain. And moreover, whenever we approach the edge of the domain, then the gradient blows up. And then sort of there's a related notion of strict convexity. So whenever we have lower growth bounds, those are sort of quantifications of strict convexity. So we want to modify these to apply to this situation where things might be infinity. And so we call a proper convex function f essentially strictly convex if f is strictly convex on every convex subset of the domain of its subdifferential f. Okay, so far so good. Now the main tool that we will use is the convex conjugate, or the differential conjugate, which is defined as we take inner products of f with x star, subtract f, and then take a supremum over x. And this gives the differential conjugate, which is a very classical tool. And one useful bit of information about the differential conjugate is we always obtain a convex function. And moreover, if f is convex, then actually it suffices to take the supremum over x in the interior of the domain. If x was outside of the domain, f would be infinity. And so this differential conjugate in the supremum that we need to evaluate would be minus infinity. So then we can always improve by taking points in the domain. And this is sort of, it's a very trivial observation, but it's somehow at the heart of why a lot of what I'm going to talk about does actually work for extended real-valued integrands. So that somehow the points where trouble might arise, those we do not really need to consider at any point. And this you can also sort of see directly from the integrand. So if I know that I have a minimizer in particular, I can assume that this integral is finite, which then means that the gradient of u has to lie in the domain of f for almost every x, because otherwise this integral would be infinite. And so that for most purposes, we can actually restrict to the domain of f, and it's just a matter of being careful about this. Now, sort of the standard example to keep in mind, if you've not seen differential conjugates before, is if you have this sort of integrand that gives us the p Laplace, so mod x to the p over p, then the differential conjugate gives you nothing but the p prime Laplacian. And moreover, if you sort of apply the differential conjugate twice, and you start with a convex lower semi-continuous function, then you get the function itself back. One more thing I want to mention here as well is, so we could also wonder, how does the notion of differential conjugate interact with the growth bounds I was talking about earlier? And it's a very simple calculation to check that if we just look at growth bounds on the first order level, so if you have a lower bound like this and an upper bound with q, this implies on the level of the dual that the bounds swap. So the bounds dualize, p turns into p prime, q turns into q prime, and upper bounds turn into lower bounds into upper bounds. In other words, then we have bounds like this. And at a later stage today, we will start wondering, so can we make similar statements about second order conditions, second order convexity conditions? Do they also dualize in this way? But for now, we will stick to just these first order conditions. And we will note that another classical tool related to the Fenchel conjugate is the Fenchel-Young inequality. So if F is convex and proper, then we have this sort of Young's type inequality, which allows us to split inner products by using F and its dual. And moreover, we have an equality if and only if the X star is in the subgradient of F. So if F is regular enough that it admits a proper gradient, so in particular, if F is essentially smooth and we have an X in the domain of F, then this applies, and we will usually use this in the way that I've written down in the example. So if you have a minimizer of the variation problem, I already said we should expect the gradient to lie in the domain of F for almost every X. And so in general, we can write down this equality to the gradient tested against the stress, which is F prime of the U or sigma, is the sum of F of the U plus the dual applied to the stress. And so in particular, whenever we want to study the Euler-Lagrange equation, then the usual approach will be to first find an approximation, and then we want to pass to the limit. And so how do we pass to the limit? Well, we use this equation. We note that this term here, by assumption, is finite, because this is nothing but the thing we're trying to minimize. And so we need to estimate this term here. And estimating this term somehow it turns out to be easier, often in the sense that it seems in practice sometimes easier to extract information about stress than the variable itself, than the solution itself. And as a sort of warm-up example, I want to talk about something for PQ growth, and we will just show that the Euler-Lagrange equation in some sense is satisfied by minimizers. And this will come from a very standard argument, and in fact, I don't think that this statement that I'm going to show you in a second is necessarily anything novel, but I think this perspective of viewing it as an expression of duality that I've not seen so much before. So we assume that P is less than Q is less than the Sobolev exponent NP over N minus P. We take a bounded W1P expansion domain. We need some regularity on our integrand, so we assume it's a Caruthei-Odori integrand, which is C1. And we more assume a convexity assumption, so that Z goes to F of Z minus lambda, Z to the P for some lambda is convex. And then we can make the following statement. So for any given ball, so this is a local statement, the stress is an LQ prime. This is how you should read this theorem. And moreover, the Euler-Lagrange equation is satisfied in some sense. So we are allowed to test against W KQ0 functions. So in a sense, this means that minimizers are very weak solutions of the Euler-Lagrange equation. And of course, it's well known that in this context, very weak solutions are not the same as weak solutions. So there's more work to be done if you want to actually have very weak solutions. Now, the proof of this is very standard and follows basically all of the theory for PQ functionals that was initially initiated by Marcellini and then further developed by a long list of names, including Acerbo, Fuschi, Mingione, and then many others. And the first step that we usually take is we build an approximation with an integrand that has P growth. So that it doesn't have any mixed growth anymore. So this I'm going to denote F epsilon. And we simply add the gradient to the power Q. And now if I have a minimizer for F, then it's possible to show that the minimizers U epsilon, they converge to U strongly in WKP. And moreover, also the integrands converge to the integrand F. And let me also mention, so we can also phrase this observation in the language of gamma convergence. Okay, so once we have this approximation, the next idea is to use duality. So using Fenchel-Young and growth bounds, we can bound from below this inner product of the stress with the solution itself. So here we should think of Z as du is the value that interests us. So we can bound this below by the P norm of du plus the Q prime norm of the stress up to some constants. And now we just look at du tested, we test the Euler-Lagrange equation on the epsilons like this. We apply these bounds. We bound things from above using standard methods and in particular using Poincare. So this explains the restriction on the Q that we needed. So we want to apply, not Poincare, Sobolev embedding at some point. And then from these arguments, we obtain the bound I've written here. So note, this is more or less exactly the same bound that we had before, but still on the level of the regularization of the approximation, so still including the epsilons. So in the next step, we need to get rid of this dependence and mean to pass to the limit. And okay, here this is actually quite straightforward. So from the bound before, we can note that sigma epsilon, the stresses are bounded in LQ prime. So in particular, we deduce that the sigma epsilon converges to the right stress in measure. We can check that the extra term we get from our regularization converges to 0 in LQ prime. In combining this information, we can pass to the limit in the Euler-Lagrange system, and we see that the Euler-Lagrange system is satisfied in the sense that it was stated in the theorem. Okay, so in the context of PQ growth, seeing that the Euler-Lagrange equation is satisfied in this very weak sense was not so difficult. Now we want to do essentially the same sort of statement, but what we would like to do is to reduce the growth assumptions. In particular, I want to drop the upper growth assumption completely, and I want to relax the lower growth assumption as much as I can. And then I want to see whether we can do an argument along similar ideas. And in order to do this, we need some more ideas from convex analysis. So in particular, we need to know a bit more information about how properties of the functional, of the integrand, pass over to its Fenchel conjugate. And in particular, the two most relevant things for us are going to be that the lower semi-continuous proper convex function is essentially strictly convex if and only if its conjugate is essentially smooth. So this will allow us to get some regularity of the Fenchel conjugate. And the second thing is, so if you assume that we have a convex function, then it's actually possible to characterize whether the domain of f is interior points in terms of this demi-coercivity condition. So you can sort of see that this is the reason why I want to consider demi-coercive integrands, is precisely because I want to be able to apply this lemma. And these sorts of statements, we really need to only be quite this careful when we want to allow for extended real valued integrands. Otherwise, the following statement is enough. So f is real valued, superlinear at infinity, and strictly convex if and only its Fenchel conjugate is real valued, superlinear, and C1. And so here I should also say the way I've written it is not quite how the implication goes. So real valued of f implies superlinear of the Fenchel conjugate and vice versa. And then the strict convexity gives the C1 smoothness. And now in our context, of course, strict convexity doesn't make any sense anymore. So we need to restrict to essentially strict convexity and then essentially smoothness. And then with this, we obtain the following theorem. So if you have an integrand that satisfies essentially the characterization, everything we needed for the characterization that we did so far. So f is convex, lower semi-continuous, proper, essentially smooth, and satisfies superlinear growth. We give ourselves a boundary datum in W11 with the additional regularity assumption that f of s times the gradient of G is an L1 for some S bigger than 1. This you could also replace with a doubling condition, but we prefer to state it this way. Then minimizers are in W11 due to the superlinearity. The direct method gives us minimizers in W11, so the problem is well posed. And we get these dual relations. So in particular, we are allowed to use U as a test function. And in the sense of distributions, the Euler-Lagrange equation is satisfied. This theorem is more or less a direct extension of a result in the paper Validity of the Euler-Lagrange system by Crozza, Christensen, and Passarelli in 2013, where the only change is that now extended real-valued integrands are allowed. Okay, so now I don't actually want to comment too much on the proof of this because it's not so different from the proof in the original paper, but instead I want to think about how much further can we push this? And in particular, can we remove the assumption of superlinear growth? So if we only assume a sort of linear growth, then the direct method gives us minimizers in BV. And so the first task we have at hand is we need to make sense of the functional. Because if you remember, this was the functional, this does not make sense for BV functions. And so we will deal instead with the Lebesgue-Serine extension of F. So given an omega compactly embedded in omega prime and G, for which we can make sense of it on omega prime, and the F is finite for this extension. Then for U and BV, we take sequences converging weakly in BV to U. And then we take the limit of the integrand evaluated along this sequence. And now we want to find the infimum of all of this. Now, the only thing that is slightly tricky about this definition is the way we impose the boundary condition. So the boundary condition we impose by ensuring that outside of the domain omega, where we originally posed the problem, the sequences need to converge to G in W11. So this is in sort of we're imposing the boundary condition in quite a strong sense. And I'm not sure whether this is necessarily the only way to define this, but I think a good sort of evidence why this is a good way of defining it is that we will be able to, with this definition, to derive a representation theorem for this integrand. So we will be able to write this in a useful way. Okay, and then with this definition, we can translate the earlier theorem about the validity of the Euler-Lagrange system into the following statement. So if you're working on the Lipschitz domain, and we have a C1 strictly convex and demicursive integrand. So note here, we don't allow for extended real-valued integrands anymore. And if you have a BV minimizer, then the stress is divergence-free in the sense of distributions. And moreover, again, we can make sense of the inner product of the stress with the minimizer itself. Okay, I want to tell you a bit about how the proof of this goes, and it goes essentially along the same lines as the P-group growth I showed you. So it should be no surprise that the first step is an approximation statement. So we need a good approximation, in this case also from below, by smooth convex integrands with linear growth. So for them, we can actually make sense of minimizers in W11. And how do we get these minimizers? Well, it's convenient to define them somehow as cutoffs on the Fenchel conjugate. So we take the Fenchel conjugate. If we dropped this maximum here, because F is convex and essentially smooth, we would just get back F. But instead, by introducing this cutoff, we get something that has linear growth and still approximates F well enough, and particularly as we let J to infinity, we recover F. And then because of smoothness considerations, we will consider some sort of modification of this. But I don't actually want to go into the detail of this all that much. Instead, I want to show you the representation theorem I was already mentioning earlier, which is sort of the next key tool in the proof. This is quite a similar statement to theorems that already existed in the literature, For example, there are much more elaborate studies of representation theorems by Fonseca and others. But in this particular case, it seems that this precise statement hasn't actually been noticed in literature so far. So if you assume that f is C1 convex and demicursive, then for u in BV, we can write the integrand as the integrand of the regular part of the gradient plus the integral of f evaluated along the singular part of the gradient. And the proof really only relies on the existence of the approximations and then the use of Jensen's inequality. And then, so this gives you one direction. In the other direction, you need to construct an appropriate sequence that actually attains the minimizer. And here, modifications with some additional technical difficulties because we need to deal with the boundary condition will give you what you want. And if you're interested in the details, then you can look in our paper. But it's really not too complicated. Okay, and now with these two tools at hand, we can sort of proceed to the main bit of the proof. And how does the representation theorem help? Well, so if you have u in BV, then by definition of the minimizer really, we can get some uj's so that f of uj converges to f of u. So not by minimizer, by definition of the extension of f, we can find the sequence, and in particular, up to a subsequence, uj will converge to some u in the sense of Young measures. So now the trick becomes we need to identify the oscillation measure, and as far as we can also the singular part of the Young measure, in terms of things that are related to u and that we can understand. And here we use the representation theorem heavily, and also it turns out to be useful to use Ekeland's variational principle. And at the end of the day, what we obtain is a sequence in W11 for which the functional converges to the value at u, which converges to the gradient of u weakly in BV. And then we have a good understanding of some of the relevance bits of the Young measure to which this gradient converges, to which the gradient converges. And in particular, I want to highlight again that we actually get convergence of the stresses. I'm missing here and almost everywhere. Okay. So now that we have a good understanding of what sort of behavior we expect as we go to the limit, as we let j tend to infinity, we want to look at the Euler-Lagrange equation related to Wj. And then we want to pass the limit. We have a good idea what sort of limit we should expect, so we can now try to actually prove something. So since fj is Lipschitz continuous and the sigma j's are in L infinity, there's no problem in writing down, even in a pointwise sense, the differential Young inequality. And now we will do what I was saying earlier. So we're interested in estimating this term. We know that this term is bounded, so we need to mainly work on this guy here. So what do? So we rewrite things in this way. Now here there are some technicalities appearing. So for this inequality, this is nothing but this. Now it turns out that the argument we need to slightly perturb the boundary conditions, but this you can just ignore for now. So just pretend that the GSJs are just G. We get some sort of error term from the regularization. Again, this term will be bounded, and so it's nothing to worry about. Okay, and then we are subtracting the value of the integrand. Again, we're subtracting something positive. This is not the term to worry about. We sneak in a factor of s in the next step, and then we use the differential Young inequality in order to pull apart this inner product into an fj star term and an fj term. And now if we choose s bigger than 1, we can absorb this term here on the left-hand side and obtain a bound of the following form. So now we've bounded the stress along the sequence in a uniform way. And in particular, this means that we can now pass to the limit in the Euler-Lagrange equation, and we obtain the theorem. Okay, I think this is as much as I wanted to say about the validity of the Euler-Lagrange system. And now I want to return to something, question that I'd briefly mentioned earlier, which is the question of, do these sort of ideas of duality also transfer to second order growth conditions? And to be more precise, let's look at the standard monotonicity that we expect. So if you ignore this term here, this would be just a normal consequence of controlled P growth from below. And now I'm asking, okay, can we actually also put the stress here? So why is this a natural thing to ask? Well, if we just view this thing here and through the eyes of convex duality theory, then what we have are, we are taking inner products of the variables against the dual variables. And now from the point of duality theory, there should be really no preference if f is convex between dual variables and original variables. After all, if you apply the dualization twice, we retain our original function. So from this perspective, it seems natural to expect that we can improve this monotonicity and get this sort of additional term, at least if we are willing to either bound, so if we are willing to bound our integrand, the dual of the integrand from below by something. So we also demand that the dual integrand has some strict convexity. And now, of course, we can then again translate this back to the primal variables, and then we obtain the following sort of growth condition. And this is why we refer to this as controlled duality growth, is because it looks a bit strange, but it really comes from this idea of, okay, what we really should be doing, instead of maybe imposing an upper growth bound in terms of Q, we impose a lower growth bound and ellipticity bound on the dual side. And then, okay, for convenience, we write this again in primary variables. And then this is exactly the sort of condition that we get. And now, with this improved monotonicity formula, which we then get, we can try to apply all the standard arguments from PQ integrands that we know well. And then we obtain actually the following theorem. So if 2 is less than P, less than Q, less than NP over N minus 2, then we have that both the V function of U and the V function of the stress, so the V function with respect to Q prime, the dual of Q, are in W12 log. And so as a consequence of this, using Sobolev theorem, the gradient of U is actually an L gamma log for any gamma up to NP over N minus 2. I want to highlight two things here in particular. So first, this range NP over N minus 2, this is bigger than the range that is known, say, for controlled duality growth. Sorry, not for control, for just controlled PQ. So for controlled PQ, it's known, I think, up to the best that I know, is Q less than NP over N minus 1 for autonomous integrands. So the range here is bigger. And the second thing I want to highlight is that we are actually including the edge case. So usually in this business of PQ integrands, the edge case is difficult to deal with. And I think in general, it's fair to say that except for a couple of specific models, usually regularity in the edge case is not known. And so with these growth conditions, we can actually deal with the edge case. That's the first thing. Yeah. And I don't want to comment too much on the proof because it really goes by the normal methods. So you use difference quotients and you really just follow what's been done in the literature. But somehow this extra regularity really just allows you, whenever you see a difference quotient hitting the integrand, to try to absorb them on the left-hand side directly, rather than having to use the growth condition first. Now, the natural question you are probably asking me is, okay, this sort of controlled duality growth gives nice results, but do we actually know examples of this? And okay, again, Yes, we do. So for example, convex polynomials satisfy controlled duality growth. So for any sort of polynomial integrand, the previous theory applies. And if you work a bit harder, then you can actually show the following theorem. So if you're in 2 dimensions, and if f is a convex polynomial satisfying an appropriate lower convexity bound, in the sense of controlled p growth from below, for some p bigger than 2, then actually U is real analytic in the interior of omega. So then you can apply the full machinery of regularity and go all the way up to real analyticity. That's what I'm saying. Okay, and I think this is actually where I wanted to leave it for today. And if there are any questions, then I'm very happy to answer them.
Yeah, so thank you very much, Lukas, for this interesting talk. Yeah, and if there are any questions, then you are welcome to unmute yourself and ask the question. Yeah, so let me maybe just start by asking what is probably a stupid question. Yeah, but so we were talking about this like lower bound with the second power. Is it reasonable to also consider maybe some higher powers, or?
Let me maybe find an example of this. So I think not really. So where these sorts of bounds in terms of the second powers, actually, I went over on. I think this is maybe a good place to explain. So where this really comes from is, if you think about convex functions, then there are various ways of characterizing them. So of course we know the first order condition. So we want f of lambda x plus f of 1 minus lambda y to be bounded by lambda f of x plus 1 minus lambda f of y. But then we also know that monotonicity in this sense, just with a 0 on the right-hand side, this is an alternative characterization. And somehow this is maybe more a characterization on the level of the derivatives. And in fact, we can deduce from this a characterization in terms of derivatives. So in terms of derivatives, convexity is characterized by something like f of y should be bigger than f of x plus gradient f of x tested against y minus x. So this would be a first order condition. And then we also have second order conditions. So we know that convexity is more or less equivalent to the second derivative being a positive definite matrix. And so then when talking about integrands, somehow it's a natural question to ask, so is the theory the same if we assume each of these convexity assumptions, or do we get slightly different different theories? Of course, if f is a C2 function or better, they all agree. But if f is not C2, then actually there are slight differences in the theory. And so the more you're willing to assume in terms of regularity in f, the stronger the results are in general.
Thank you. Maybe some other questions? So in the meantime, you can also take a look at the chat. There are some messages for you. And I think that if there are no other questions, then I can just pass the word to Lukas, who will maybe invite you for the next seminar.